So if you keep an object in a flow field, okay, there will be only one force, that is called resultant force. Okay, so there is no lift, there is no drag. So practically there will be only one force, that is called resultant force. The object can be of anything, bluff body, streamline body, depends upon that. You will get only one force. Okay, so here I have taken the flow over the aerofoil at an angle of attack. So that one force is called resultant force. Okay, and depends upon the holding position, there will be additional moment. Okay, you know the CG point of CG, right, where the total force act. Similarly, this is the 2D object, so there is no weight. So here the center point we are calling as center of pressure, where the total force is acting. Okay, if you take the 3D object where the total weight is acting, that we call it as CG, center of gravity. This is the 2D, so theoretically there is no weight, and here the point at which the total force is acting is the center of pressure. Okay, so if you hold this aerofoil, we have to fit this, assume the model is fitted into the wind tunnel. Okay, if you fit this in the center of gravity, center of pressure point, there will be only one force. But if you fit this in some other point, then there will be additional moment. Okay, so if you keep an object in a flow field, there will be only one force, that is resultant force, and depends upon the holding position, there will be an additional moment. Is that clear? Hello? 85 student joint. So if you
Yes, sir.
don't,
Yes.
okay. And the resultant force is due to the two components. One is pressure, another one is shear stress. Okay, so the around the aerofoil or any model, there will be a pressure distribution and there will be a shear stress distribution. Due to these sources only, we are getting that force. Okay, so these two are the sources. So sources of the force is pressure distribution and shear stress distribution. And you know pressure will act normal to the surface, and shear stress will act tangent to the surface. Okay, so pressure will act normal to the surface, shear stress will act tangent to the surface, and depends upon the angle of attack and the profile, you will get different distribution. So these two are the sources, pressure and shear stress. And as I said, there is only one force, that is called resultant force. Then for our convenience, we are resolving that resultant force into lift and drag, or normal force and axial force. Okay, so if you are resolving this R with respect to this free stream flow velocity, that is called as lift and drag. So lift will be normal to this free stream flow direction, drag will be parallel to the free stream flow direction. Is that clear? So resultant force we are resolving into lift and drag, or normal force and axial force, depends on our convenient. So if you resolve this resultant force with respect to the free stream velocity, then it is lift and drag. And if you resolve this R with respect to this chord line, then the normal force will be normal to the chord line, and axial force will be parallel to this chord line. Okay, so both are the component of R. Okay, and we are resolving with respect to free stream velocity and chord. Is it clear? These four forces, lift and drag, are normal force and axial force. So you may ask, what is the use of this normal force and axial force? Directly we can find the lift and drag. The purpose is, compared to this lift and drag, finding this normal force and axial force is easy, because it is with respect to the chord line. If you are fitting one model in the wind tunnel, okay, if you don't know the angle of attack also, you can find this normal force and axial force. Okay, but here you should know the exact angle of attack. If you don't fit the model in a proper angle of attack, you will get wrong lift and drag. But here you can get the proper trend. If you are drawing for example normal forces as angle of attack, okay, you are simply changing for different angle of attack, and simply if you plot the what is it, if you plot the curve, it won't be wrong. Okay, because there is no angle of attack term here. But at last in the paper, research paper, everywhere you see, it will be in terms of lift and drag only for understanding. But this normal and axial force, it will be used in between the calculation. From pressure and shear stress, we will find the lift and drag. But in between, we will find this normal force and axial force because it is easy to resolve. Okay, for that purpose, they introduce this normal and axial, but mostly you will resolve into lift and drag. And this is the derivation. So once you know the pressure distribution and the shear stress distribution on the aerofoil, we can find the CL and CD of the object. Okay, so in this derivation, our aim is to find the CL CD if you know the pressure and shear stress. But directly we are not relating CLCD with pressure and shear stress. First we are finding CLCD in terms of CN and CA, that is normal force coefficient, axial force coefficient, because it is easy to resolve. Then we are writing this CN and CA, normal force coefficient, axial force coefficient in terms of pressure coefficient and centrifugation coefficient. Is that clear? So this is the final finding. Once you know the CP and CF, we can find the CLCD. But in between, first we are writing CLCD in terms of C and CA, then C and CA in terms of pressure and shear stress. This is the step. Is it clear? Now we can go to the derivation. So this is the resultant force. So we can resolve into lift and drag or normal force and axial force. Okay, and our aim is to find the lift and drag. So first I am writing lift equation in terms of normal force and axial force because it is easy to find. Okay, and here assume the angle of attack is alpha. Then what is the angle here? Anybody? So free stream velocity and the chord line, the angle is alpha, angle of attack. And what will be the angle here between this chord line and the drag? Are you listening or not?
Yes, sir. Yes, sir.
So this is one inclined line, and this is one straight line. You know both sides the angle will be same, right? Okay, if you mark alpha here, this is horizontal line, this is inclined line, then this here also angle will be same, right? So if you mark alpha here, then here also the angle is alpha. Okay, then what is the angle here, lift and normal force? So everyone is attending or sleeping? Ajay?
Attending.
Okay, good. I'm just asking normal, what is it? What you studied in EG or school days only, right? That only I'm asking. No one is replying. So what is the angle between lift and normal force here? Ashish, Ashish Joshi,
Yes, sir.
what is the angle? So here also it is alpha. Okay, you see this is lift and drag. Okay, again both are 90 degree to each other. Again normal force and axial force, that is also 90 degree to each other. That means this is also 90 degree to each other. Okay, so if here it is tilted to alpha degree, then here also it will be same degree, right? Okay, this right angle, the L shape is just turned to the same degree on both sides. So here alpha means here also alpha. Okay, so once you know this 3 degree, the 3 deflection angle, you can write the lift and drag in terms of normal force and axial force. Again you see, instead of L and D, I have mentioned L dash D dash. The reason is, for 3D object, we will mention lift as L, drag as D. Okay. For 2D objects, we will mention L as L dash, D as D dash. So L dash means lift per unit span. Okay. So this is the 3D wing. So this is the chord, this is the span. Okay. But if you take 2D, so this is the chord, and we will assume there is a unit distance in this direction, right? Okay. That's why per unit span we are taking. Okay. So 2D means L dash, D dash we will mention. 3D means L and D caps. And in terms of CL, if you want to write, for 3D it is capital CL, capital CD, and for 2D it is small letter CL and CD. That's it. Okay. So now we can write this L equation in terms of N and A. What we have to do, simply we have to resolve this N and A in the L direction. Okay. So here it is alpha, here it is alpha, and this is the sign convention, we can use it, plus plus minus minus. Now you see N dash cos alpha, and it is upward, so it is positive. Okay. I am resolving N and A in the L direction. So N dash cos alpha, that is in the upward direction, so positive. Then A dash sin alpha, but it is downward, so it is negative. Okay, that's it. We found the L equation. Then similarly, we have to find the D dash equation. Is that clear? L dash equation.
Yes, sir.
Okay. Then D dash, same way, we have to resolve this. Sorry. Same way, you have to resolve this N and A in the drag direction. So here it is alpha, here it is alpha. Now if you resolve, so N dash sin alpha. Okay, this side it is positive, that is right hand side. So it is N dash sin alpha. Then this one is A dash cos alpha. Both are in the right hand side, so both are positive. Is it clear?
Yes, sir.
Okay. So N dash cos alpha, then this is A dash sin, N dash sin alpha plus A dash cos alpha, both are positive. So in this way we got L and D in terms of normal force and axial force. Then I am going to write lift and drag in terms of CL and CD. You know the general relation. Lift is equal to half rho V squared S CD. This is for the 3D model. And if it is for 2D, then it should be L dash is equal to half rho V square. Instead of S, I am going to take only C. Okay, because for 3D it is C into B. For 2D it is only C into 1. Okay, so only C into small cd. So this is the equation. Okay, so I have to convert this L dash into CL now. And this thing you studied in your fluid dynamics, how to write CL, CD, CNC and all. Yeah, same equation. Right. Okay. So L dash is half rho V square CCD, and this half rho V square is the dynamic pressure. So instead of half rho V square, we are denoting this as Q infinity CCD. Sorry, CL, right? There I am writing CD, no one is telling that is wrong. So lift means CL, right? So now if you want to find CL, then you have to rearrange. You will get CL is equal to L dash divided by Q infinity C. The same manner you can find it CD, CN, CA and all. Okay. Coefficient of lift, coefficient of drag, coefficient of normal force, coefficient of axial force. So everything you can find it. So this one you have studied already. And similarly, CP formula. So assume this is the aerofoil, and here we have the free stream flow with a pressure P infinity, and everywhere you will get different pressure. Assume I am going to find the Cp in this point where the pressure is Pu, then the Cp formula will be so Pu minus P infinity divided by Q infinity. This is the Cp formula. Okay, Pu pressure on this point minus free stream point divided by Q infinity dynamic pressure. This is the Cp formula you studied. Then Cf is simply shear stress at that point divided by Q infinity. Okay, so this is Cp Cf equation. Okay, so Cpu means Pu minus P infinity by Q infinity. Cpl, that is U means upper surface. If you are finding on the lower surface, then it is, for example, here means PL minus P infinity by Q infinity. Is that clear? These equations, CL,
Yes,
CD, CP, CF, everything. Okay. So using this, now we can convert this equation into CLCD. What you have to do? Simply you have to divide this by Q infinity C on both sides. Okay. So if you divide this L dash by Q infinity C is CL, and N dash by Q infinity C is CN, A dash by Q infinity C is CA. Okay. Similarly here also, if you divide by Q infinity C, you will get these two equations. Is that clear? Okay. So next step. So as I said, now I found CL in terms of C and CA. Next one is C and CA in terms of pressure and shear stress. This is the second step. With that, we can finish this derivation. Okay, so first step is over. Now this we have to find it. C and CA in terms of pressure and shear stress. Okay, so here we are finding. So this is the flow over the aerofoil. First I am taking one small area ds. Okay, assume the length varies along this s direction. I am taking one small area ds on the upper surface, and this line shows the normal force direction. This shows the axial force direction. Okay, normal force vertical, axial force horizontal, and assume this small panel I have taken, right, where the angle is theta. Okay, the slope you can find it. So it is inclined to the angle theta. Okay, so here also we are getting theta, here also we are getting theta. Similarly, in the bottom surface also I am taking one small panel. There also I am marking pressure and shear stress. Pressure will always act normal to that panel. Shear stress always will be tangent to that. Here also pressure is normal, shear stress is tangent. Okay. Here also we have some inclination. So this may be the theta 1, this may be the theta 2. Actually for aerofoil, along the surface, the theta will vary everywhere, right? If it is a flat plate, the theta is same above and below. Anywhere you measure in this point or this point, anywhere you measure, theta will be constant. But if you take the aerofoil, theta will be different for every points. Okay. So here you may have theta 1, here you may have theta 2, for example. Now this is how pressure and shear stress distribution will be there. Is that clear for the aerofoil? Any doubt here? So any panel you can take. Okay, so pressure will act normal to that, shear stress will act tangent to that. Okay, and we are going to find the normal force and axial force. So I am taking vertical horizontal, and this angle is theta. This may be theta 3. Like that you can draw anywhere. Is it clear? So this is an important hallmark, this derivation. Okay, so now we have pressure and shear stress distribution on upper and lower surface. Actually, I am going to find it for only this small space, then I can integrate it from the leading edge to trailing edge. Here also, I am finding only for this small section, then I can integrate it for the leading edge to trailing edge for the complete aerofoil. Okay, so now I am going to find a normal force in terms of pressure and shear stress. What you have to do is simply you have to resolve all this p and tau in the n direction. Okay, assume now I am finding the dn only for this small portion. Okay, now so first this component we can take, that will be minus pu cos theta, right? If you resolve vertically, because it is inclined, that is downward, so I am putting minus sign. So this pu, if you resolve in vertical direction, it is pu cos theta, it is facing downwards, so minus sign, and this is the pressure component. But what we need is the force. So force means it will be pressure into area. Okay, so this pressure component into this pressure is acting on this small area ds. Okay, so this I have to write it as minus pu cos theta ds. This is the first component. Okay, then I can resolve this tau u. So this will be resolved like this. I have to resolve, that is minus tau u sin theta, this is shear stress, into area. Okay, so minus tau u sin theta ds. So upper surface we resolve, then come to the lower surface. This pl we can resolve like pl cos theta into ds, pressure into area, and this acting upward direction, so positive. Then this one vertically we have to resolve, then it will be, I think, minus tau l sin theta ds. Like that you have to resolve. Is that clear? Resolving that pressure and shear stress.
Yes, sir.
Okay. So force means pressure into area. You should not forget this ds. Okay. You should not simply write p into cos theta alone. You have to multiply with the area acting on that. Okay. Then for the complete n dash, we are integrating all those terms. Okay, from leading edge to trailing edge. So you will get this final equation. Is that clear? So initially I have taken one small portion. Then for the complete aerofoil, for complete normal force, we have to integrate these terms from the leading edge to trailing edge. The same way, now I am going to find this axial force. Okay, now we have to find this axial force. In that case, all this pu, tau u, pl, tau l, everything has to be resolved in this horizontal direction. Okay, so see, if you resolve, it will be minus pu sin theta into ds, because it is, this is a sign conversion, so it is acting left hand side, so minus pu sin theta ds, and this one like this we have to resolve. In that case it is positive tau u cos theta ds, and this if you resolve, it has to come like that. That means positive pl cos theta ds, and this one horizontally we have to resolve. That means positive tau l cos theta ds. Is this correct? This is sin theta, right? Okay. Horizontally if you resolve, it will be pl sin theta. So see, minus pu sin theta ds, positive tau u cos theta, positive tau l cos theta, then pl sin theta. Then if you integrate from leading edge to trailing edge, we can find the total axial force. Same procedure. Only thing is, here we resolved vertically, here we resolved horizontally. So these steps are almost equal to that what you studied in the engineering graphics, resolving the forces. This clear, right? So we are getting two equation, n dash a dash, in terms of pressure and shear stress. So what we are found is this for the thick aerofoil because where the theta is different at every point. And in aerodynamics, so we are going to assume that is include lot of assumptions. So we are going to assume the aerofoil is very thin so that the upper surface and lower surface coincide on this camber line. So what we finally take is only this camber line, okay, in the aerodynamics 1. So whatever the results we are getting in this aerodynamics 1, it won't be accurate. It just gives you some initial idea, okay, just approximation methods. Using that you will get some initial idea, okay, all these aerodynamics 1. So if you take thick aerofoil where the theta is different at different location, then this equation will work. But if you take the thin aerofoil, then in this case, if you take one small section, the above and below the theta will be same. Okay. So in that case, we can simplify this equation to like this. That is theta is constant. In that case, if you take cos theta outside, we can write PL minus PU into cos theta ds. Okay. Similarly, here I can write it as tau u plus tau l into sin theta ds. Okay. For thin aerofoil, the theta is constant. So we can take cos theta, sin theta commonly outside. So we are simplifying n dash a dash for the thin aerofoil. Is that clear?
Yes,
So
sir.
first is black color equation is for thick aerofoils. Anywhere if you take here different theta, but here one line if you take along the chord line, it is up and above and below, it is same theta only. Now this is our final n dash a dash equation for thin aerofoil. And now we can convert this n dash into Cn. Simply we have to divide that by Q infinity C. Okay, so this is Cn, and here you see, okay, so Cf means tau divided by Q infinity, Cp means P minus P infinity by Q infinity, that is Cpu means Pu minus P infinity by Q infinity. So this C term I am taking outside, so it is 1 by C in the remaining equation. And now this I can write it as CFU and CFL, coefficient of friction on the upper surface, coefficient of friction on the lower surface. But this one directly I can resolve because I need the P infinity term. Okay, so to convert this, I am introducing minus P infinity plus P infinity in this equation. Okay, now we can write PL minus P infinity one term. Then from this minus Pu and plus P infinity, if you take minus outside, it will be Pu minus P infinity. That is, we have PL minus Pu. So include minus P infinity plus P infinity. Then rearrange, it will be PL minus P infinity. Remaining will be minus Pu plus P infinity. And from this term, take minus outside. Then you will get Pu minus P infinity. Is that clear?
Yes, sir.
Okay. So now I have two terms, PL minus P infinity, Pu minus P infinity. That I can write it as CPL minus CPU. Okay. So this is CPL. This is CPU. That's it. This is the final CN equation in terms of CPL and CP and CF. The same way you can write CA, same procedure. So for what is that? For thin aerofoil, theta is constant. Then divide this by Q infinity C. Rearrange, you will get this equation. So once you know this CN and CA, straight away you have to substitute in this CLCD. With that, the derivation is over.